So, number 5 is, I guess, where we left off. So, the moon takes 27.32 days to revolve around the Earth once. And the moon is 4.1 times 10 to the 7th meters. I guess it's a good idea to write down the units. Meters from the center of the Earth. If the International Space Station makes an orbit around the Earth in 90 minutes, don't forget this is in minutes, this is in days, right? How far away is the International Space Station, right? So they're looking for, right, C, right? So we can actually use the, so here we can do the Earth. Here's the Earth, right? Here's the International Space Station, right? And here's the moon, right? So the distance from the center of the Earth to the moon is C moon, right? Which is equal to 4.1 times 10 to the 7th meters. And we want to find out what is the C space station, right? SS, ISS, right? So we're looking for that. So the T moon is equal to, right, 27 whatever days, right? So I guess we can use that, I guess, right? 27.32 days. Perhaps maybe we should change that into minutes, okay? Or maybe even to hours, because this 90 minutes is basically same as 1.5 hours. So if we multiply this by 24, right, then we can get this in hours. And if we multiply that out, I think we'll get something like 655.68, right? So 655, right, 655.68 hours. All right, so that's the T moon. All right, and T ISS is equal to 1.5 hours. So we can use Kepler's third law, right? Where you can say C ISS cubed over T ISS squared is equal to, right, C moon cubed over T moon squared. All right. We are looking for C ISS, right, which is equal to then, right, cube root of C moon, right, cubed over T moon squared times TISS squared. Okay, so if we can plug and chug, right, cube root of then, right, C moon happens to be 4.1 times 10 to the 7th cubed. Divide that by 655.68 squared times times 1.5 squared. Okay? So if you work that out, I think you get something like cube root of, right? I'm going to just give you, if you work this out, you're going to get a, 3.61 times 10 to the 17th, okay, meters cubed, I guess. And that comes out to, if you cube root it, you get 7.12 times 10 to the 5th meters. You actually, if you get the digits, you get 711,841.7 meters is what you actually get. But if you want to put it in a scientific notation, this is what you get. All right. All right. Next, Jupiter is about 5 times, right? 5 times farther away from the sun than the Earth. What is Jupiter's orbital period in years? Now, this feels like they didn't give us too much. But if you think about what they're saying, we could say we already know the period of Earth. Period of Earth is 1 year, 1 Earth year, basically. Okay, and the sea Earth, which is the distance from the sun to Earth, we'll just consider that as 1 astronomical unit, 1 AU, right? They're looking for the period of Jupiter, right? And we know that the semi-major axis of Jupiter is 5 AU, which is 5 times, right? So 5 AU, right? Maybe I should have put that in purple, sorry. 5 AU, right? So this is actually pretty simple when you think about it, right? So you can say, right, C Jupiter cubed over T Jupiter squared is equal to, right, C Earth cubed over T Earth squared. We're looking for T Jupiter, right? So if we solve for T Jupiter, we're going to get T Jupiter squared is equal to, right, C Jupiter cubed times T Earth squared over C Earth cubed. So T Jupiter is equal to square root of C Jupiter, which is 5 AU, right, cubed, right, times 1 AU squared. Oops, got that a little too long there. And I'm sorry, that's not right. 1 year squared, 1 year squared, and 5 AU cubed. No, that's 1 AU cubed, sorry. I'm getting all confused here. So this should be 1 year, 1 AU. Okay. So what happens? Well, AUs get canceled out, right? And then we get 5 cubed is 125, right? Times 1 year, right? Squared. And then you have to square root this sucker. Therefore, the period of Jupiter is equal to right? Square root of, right? 125 years squared, which is 11.18 Earth years, right? So it takes 11.18 Earth years for Jupiter to go around the Sun. Okay. All right. Any questions? Okay. Good. All righty. Let's take a look at number 7. So that was not as hard. That was pretty easy. Now, number 7, 8, and 9 can be all put together as one problem with subparts. All right. So, number 7 states, in a galaxy far, far away, planet X orbits the star QX392, which has mass of this many, right? So this is the star, right? Kilograms, and it takes planet X total of 1.6 Earth years to orbit its central star, which is this. Right? So this is the mass of the central. This is the central mass where the star is actually going. What is the average distance from the, I guess not the sun, but I guess this should be more like QX392, right? That's what it should be, right? So, here what we can do is, right, we can say C cubed is equal to, right, T squared, right, times G times mass of the central star divided by 4 pi squared. Okay? So, we must, when we use this equation, we must use this in seconds, this in meters. All right? Therefore, I even gave you must convert into seconds. 1.6 Earth years, right? So we have to convert that. So 1.6 Earth years, if we multiply that by, right, 365.25 if you want, days per 1 year, right? There are 24 hours in 1 day. And then there are 3,600 seconds in 1 hour, right? So if you work that out, you're going to get something like huge, right? You're going to get something like, well, let's take a look. 1.6 times 365.25 times 24 times 3,600. Yeah, you're going to get something big. So you're going to get like 50492160. All right. So this is the period of that planet X. Okay. So this is a TX, CX, TX. So here we could put this in and say 50492160 squared times. G is really a constant that you need to just know. And I think I gave you that formula sheet, right? And G happens to be 6.67 times 10 to the negative 11. Okay? So we can say 6.67 times 10 to the negative 11th. This is always going to be the value. This value does not change. The mass of this central star, or the central mass, is 6 times 10 to the 30th kilograms. This is a huge unit, like it's newtons times meter square per kilogram square, so I'm not going to write that in there. Whole thing divided by 4 times pi squared. This square does not square the 4, okay, by the way. So if you work that out, I think you get something like, a 1.02 times 10 to the 34th or something like that. Right. So here, let's square this, right? And then multiply that by 6.67 EE to the negative 11th, right? Times that by 6 EE 30th. And you get something like 1.02, right, times 10 to the 36. Divide that by 4 pi squared. So when you divide that by 4 pi squared, make sure you do 4 times, right, pi squared. No, I didn't want to do it that way, sorry. 4, let's divide by parentheses. 4 times pi squared, right? That's what you should do, right? And then you get something like c cubed is equal to 2.58, right, times 10 to the 34th. So cx is equal to cube root of that, which is 2.58 times 10 to the 34th. So if you cube root it, you could go to math, and then you do cube root, right, of the answer. And then you'll get something like 2.96, right? So get 2.96 times 10 to the 11th meters is how far away that planet X is from that QX 392. All right? All right. So a lot of algebra, basically. Okay, just make sure you are following step by step and be meticulous about it rather than trying to rush it, because it's not that hard of a math. All right. Now we can use this information, right, for number 8. So planet Y, also orbiting QX 392, is twice the average distance away from the star than planet X. What is its period? Right? Now, they want this in either in Earth years or in seconds. Now, you can choose either one. Now, we already know that Cx is equal to, right, this much. But we can say, since they gave us twice the average distance away, is this, or you could just say just Cx if you want to, right? I don't know if that makes sense, but could just say cx. So you can say cx, you could just simply say 2.96 times 10 to the 11th if you want to, right? And tx is equal to, right, 1.6 years. Then cy is equal to 2 times 2.96 times 10 to the 11th. Right? Divide that by, well, ty is what you're looking for. Right? So you can say cx cubed, right, over tx squared is equal to cy cubed over ty squared. Right? So if you were to solve for ty, right, then you can say ty squared is equal to, I'm going to bring that to the other side, cy cubed over cx cubed times tx squared. So you can say cy is just simply 2 times, right? 2 times 2.96 times 10 to the 11th cubed over, right, cx, which is 2.96 times 10 to the 11th cubed, right, times tx, which is 1.6 years squared. So if you think about this cubed, they'll cancel out, which will just leave you with 2 cubed for this whole fraction, right? So that will be 8, right? That will be 8 times 1.6 squared, right? Because this cubed and this cube will cancel out. Okay? Therefore, ty is equal to square root of this, which is 1.6 squared times 8, which comes out to 20.48. So when you take a square root of that, your ty comes out to 4.53 years. Now that's a lot easier than working with seconds, I think. Okay. All right. Now let's take a look at number 9. Okay, number 9. Planet Z, also orbiting the same central mass, the star QX392, has a period half of that of planet X. What is planet Z's average distance? Okay, again, we can use, right, Cx, which is equal to, again, Cx, right? So let's do it this differently this time, just Cx. We'll just call that 2 point whatever as Cx. Like we'll call this right here just Cx. Okay? And then Tx is, right, 1.6 Earth years, right? Then CZ is equal to, right, question mark. And TZ is equal to, let's say, half, right? So 1/2, or 0.8 Earth years. Okay? So we'll find this CZ in terms of CX and then just multiply that by 2.9 times 10 to the 2.96 times 10 to the 11th after we get it. All right? So let's see. Here we say CZ cubed over TZ squared is equal to, right, CX cubed over, right, TX squared. Therefore, right, CZ cubed is equal to, right, CX cubed times, well, let's write that, over TX squared, which is 1.6, right, times TZ squared. So that is equal to, CX is just CX cubed, TX is 1.6 squared times 0.8, right? 0.8 squared is what we have. All right. Therefore, if you work it out, what do you get? Well, I think you get CZ cubed comes out to, right? Well, this becomes, just stays as CX cubed, right? And what about this? This becomes 1/2, right? Square that, you get 1/4. So you get CX cubed over 4. So when you cube root this, so CZ is equal to then cube root of, right, CX cubed over 4, and that comes out to basically, right, CX over cube root of 4. That is, right, 2.96, right? 2.96 times 10 to the 11th divided by cube root of 4. What is cube root of 4? Right, so math, cube root of 4. And I get 1.587. So what is that, John? Right, so you get 2.95657 EE 11, divide that by 1 point whatever, right, the answer, and I get 1.8, right? So 1.86 times 10 to the 11th meters.
Mr. Kemp,
Yeah?
don't you need a cubed root? You wrote a square root.
Yeah, I should write down cube root. You're right. I forgot the 3. Thank you. Yeah, cube root. It should be cube root, definitely. All right. So it's just another variation of showing how it can be done without using all these crazy numbers in there to make it look big, right? So again, do whichever you feel comfortable You know, you can use the letters or you can use numbers, whichever you feel more comfortable. All right. Any questions before we move on to number 10? All right, so let's go on to number 10. Now, Mars has two moons, right? Phobos and Deimos. Now, fear and panic. The companions of Mars, right? Basically, the god of war. Deimos has a period of 30 hours and 18 minutes, and the mean distance from the center of Mars to Deimos to be 2.3 times 10 to the fourth kilometers, right? So they have minutes and kilometers as the unit, okay? So keep that in mind. If the period of Phobos is 7 hours and 39 minutes, what mean distance is it from the center of the Mars, right? So let's take a look. So Mars is a red planet, right? So we'll do a red planet. Here's Mars. Here is, well, Phobos and Deimos. So I'm going to say this is C Deimos, okay? And that happens to be 2.3, right, times 10 to the fourth kilometers. And the period of Deimos is 30 hours and 18 minutes. So maybe it's a good idea to convert that into just minutes. All right, we'll do that. And then we're looking for, right, C Phobos, right? And we know the period of Phobos happens to be 7 hours, 39 minutes. All right? So let's convert the period of Phobos, which is 7 hours and 39 minutes. If we convert that, what do we get? So 7 times 60, right, which is 420, 420, right, plus 39, and we get 459, right, for the minute wise, right? All right, so 459. And for oops, that's the wrong color. No, okay. Period of Deimos happens to be 30 hours and 18 minutes, and that is 30 times 60 plus 18. So I got 1818, right? All right. So if we use these times, which is consistent now, right? Because this kind of mixed units is really pain in the butt to work with. Now, what you could have done was you could have changed the 18 minutes into hours and then used as a fraction, as a decimal for 30 point whatever hours, or same here. 39 divided by 60, and then you use that 7 point whatever hours. You could have used that too, right? But I think this is much cleaner. Okay. So now we can say, okay, all right, so C, oops, C, let me use C phobos cubed over T phobos squared is equal to C deimos cubed over T deimos squared. Okay? So C phobos cubed is equal to C deimos cubed over T deimos squared times T phobos squared. So if we substitute in some values in here, so C deimos is 2.3 times 10 to the fourth cubed. Divide that by T, which is 1818 squared, times 459 squared. All right. All right. So what happens if you do that? That's a lot of mess, right? So you get 1818 squared. You get that. So 459 squared, divide that by the answer, right? And then multiply that by 2.3 EE 4 raise that to cubed. Yeah, I get, so all that mess turns into 8.47 times 10 to the 24th. So if you cube root that, let's see what we get. Okay, something's wrong. All right, let's rework that out. Something's not right. Hold on. So 2.3 EE fourth. I know I forgot to put them in parentheses. 2.3 EE fourth close parentheses cubed, right, times 459 squared, right? Divide that by 1818 squared. Okay, so that comes out to, yeah, so this sounds more like it. So this should be actually 7.756 times 10 to the 11th. So 7.756 times 10 to the 11th. And if you cube root that, right, yeah, you should get 9,187.7 kilometers. Therefore, you get 9.2 times 10 to the third kilometers. So I gave you the answer so you guys can check. As you notice, I even made a mistake just because I forgot to put a parentheses around the cube. And, you know, I was just, so even that little tiny thing, when I don't put a parentheses around that, that's when I get in trouble, right? So be careful. All right, so that's that. So again, I'm giving you the answer so you can check, okay? All right, let's take a look at number 11. Number 11. A Martian lander is to be placed in orbit around Mars at a mean altitude of 100 kilometers, or this plus the radius of Mars is what this should be, right? So it's 3,490 kilometers from the center of the Mars. Okay? So here, this is the radius of Mars, and this is the altitude of the lander, I guess, right? Let's see, I need a different color. So Mars lander is this, and this is the altitude, right? The altitude is 100 kilometers, and this is basically C. This is C of Mars lander, and that is 3,490 kilometers. Okay? All right. So Mars lander. Now you can use either one of these variables. So you could compare it to the Phobos, or you can compare it to Deimos, right? So since this is given to us, so we don't want to double jeopardize ourselves. If we calculated this wrong and if we use wrong value, this will be also wrong. But this is given to us already, so this is not a wrong value. So maybe we should use this instead of what we calculated. All right, so let's compare it to Deimos. All right, so here we're Deimos, C Deimos cubed over the period of Deimos squared is equal to C Mars lander cubed over the period of Mars lander squared. If we solve for Mars lander period squared, right, then bring this to this side, and we have, right, C Mars lander cubed times, right, T Deimos squared over C Deimos cubed. Okay? Now, which one do we want to use? Let's use minutes, so we can actually calculate the minutes and then convert that into either seconds or hours. It doesn't matter. All right? So we're going to use minutes since we already have that calculated there. So T Mars lander squared is equal to C Mars lander, which is 3,490 kilometers cubed, times, right, T Deimos is 1818, right, squared over C Deimos, which is 2.3 times 10 to the fourth kilometers cubed. Okay? So if you work that out, okay, let's see what we get. So we get 3490 cubed, right, times 1818 squared, right, divide that by, now don't forget the parentheses again, like don't make the mistake that I did, 2.3 EE to the fourth cubed. Okay, so what do I get? I get something like 11,547, right, 0.3. So T Mars lander is equal to square root of that, 11,547.3, and that is equal to, right, that comes out to 107, right, 107.5. So, minutes. So if we want to convert that into hours, all we have to do is just divide that by 60, right? And you get 1.79 hours, right? Or if you want to multiply that by, 60 and you get seconds, right? Or if you multiply that by 3,600, then you get seconds, which is 6,447.5 or 4,448 seconds. Same thing. All right? All right. Last one. All right, last one. All right, so the planet Mercury. All right, the planet Mercury takes 88 days to go around the sun. So we can say planet Mercury T Mercury 88 days. Right? Then what is the distance from the center of the Mercury to the center of the sun? So they want to find out what the distance C Mercury is, right? So, well, we can use a lot of things actually. We can use the Earth, we can use the Moon, right? We can use Mars, whichever. We know so much already. We can use, but I think the Earth is the easiest because we already know how many days it is, right? We know how far it is, right? So let's do that, all right? So I think I gave you I didn't give it to you, I guess, huh? Well, maybe it's a good idea we should find that out, huh? The T Earth is 365 days, right? We know that. C Earth, I think you could just Google it actually, right? What is the distance from Earth to, let's see. Distance from Earth to Sun. All right. In meters, right? So it looks like 149.6 billion meters, right? So 1.496 times 10 to the, now billion is ninth, 10th, 11th, right? 11th meters is how much it is. So that's the distance from Earth to Sun. All right. So if we know that, we can say, maybe we should write that down here, right? Distance Earth to Sun is equal to 1.5 times 10 to the 11th meters. All right. So we can now use right? C Mercury cubed over T Mercury squared, right, is equal to C Earth cubed over T Earth squared, right? So we can say C Mercury cubed is equal to, right, C Earth cubed over T Earth squared times T Mercury squared. So let's put some numbers in there. C Earth, so that is 1.5 times 10 to the 11th cubed, right? Divide that by T Earth, 365 days squared times 88 days squared. All right. So if you work that out, you're going to get 1.5 EE. Again, I forgot to put that in parentheses. So 1.5 EE 11 close parentheses cubed, right? That's important, right? Times that by 88 squared. Divide that by 365 squared. So I get something like 1.96 times 10 to the 32nd. So C Mercury is equal to cube root of 1.96 times 10 to the 32nd, right? And that is equal to, well, let's do that. So math, cube root of that number. And I get 5.8 times 10 to the 10th. So 5.8 times 10 to the 10th meters is what I get. All right. All right. Any questions? All right. Good. So I'll stop the lecture here, and then